Okay, so now we talk about electronegativity. So this is where we start getting into some of the fun stuff here. So put aside shapes and Lewis structures for the moment. We'll come back to them, but I got to talk about electronegativity first. So think about a bond between two hydrogen atoms or two fluorine atoms. Now, the reason this bond is forming is because a pair of electrons, or because each of these atoms needs these electrons to complete its octet. And the reason, trying not to anthropomorphize the elements too much, the reason this happens is because it's being attracted to the nucleus, the protons in the nucleus, so that's what's causing this attraction. Now, in hydrogen and hydrogen, or I should say this, two identical atoms are going to share exactly equally. These two fluorine atoms, they share those two electrons exactly equally. Remember how I was kind of drawing orbitals before? I was drawing orbitals like this, and it was just describing where the electrons are spending its time. We can also kind of illustrate something by showing sort of the electron density. If we kind of did an orbital for the whole thing, the shared electrons are being shared equally across the two, and I didn't do a good job of showing that, but they're spending equal time around each of the atoms, right? They're spending equal time, and so there's an equal sharing, more or less. Actually, exactly equal in the case of these elements, when they have the two identical atoms. Different atoms attract differently. So when you have hydrogen bonded to fluorine, it turns out that the electrons spend a lot more time hanging out around the fluorine than they do the hydrogen. Let me exaggerate that more so it doesn't just look like my normal bad drawing. Here's the nucleus for hydrogen, here's the nucleus for fluorine. It looks like this, right? The electrons are being pulled away from hydrogen towards the fluorine. Fluorine, for a lot of reasons having to do with the balance between its nucleus and its valence electrons, is much better at pulling covalently shared electrons towards itself than hydrogen is. The tendency is called electronegativity. Atoms that are more electronegative are better at pulling electrons towards themselves. It's like sharing. The analogy I use, which is kind of funny, if you have two children that maybe don't share very well, if they are about equal size and age, then they share much better, because one cannot just wrest a toy away from the other. But if you have one that is bigger than the other, or just more aggressive, they might end up with that toy a little more often, even though they're, quote, sharing. And so, to kind of give you a general trend, so this trend of electronegativity is based on, you can kind of predict it from the columns and the rows of the periodic table. So, and it changes in sort of a regular way. And I'll even talk about why, just to give you a little bit of a backing, but you don't need to know why. You just need to know what the trend is. So, going down a column, electronegativity decreases. So if we look at the periodic table, so fluorine is very electronegative. It's very good at taking electrons from its neighbors and not completely yanking them towards itself. Well, I'll get to that actually in a minute. But it's better at taking electrons from other atoms than chlorine. And chlorine is better than bromine, is better than iodine. Nitrogen is better than phosphorus, is better than arsenic. So as you go down the table, they get less electronegative. Now, we don't really talk about the electronegativity of the noble gases at all because they don't really make bonds at all. So we're not talking about them in this context. So, just the other elements. Now, what was I going to say? So, and the reason this happens, the reason you get this effect is because if you think about chlorine, you have the nucleus and you have its electrons, and its full shell is the second shell. If you go down to chlorine, its full shell is the third shell. And so what's happening is that they're getting the valence electrons that this nucleus is trying to influence is getting farther and farther away. Yes, there are more protons in chlorine than in fluorine, so it's more positive. But it turns out that the decay of attraction is related to 1 over the radius, the distance squared. So the ability for the nucleus to attract electrons goes down pretty rapidly as you go to outer and outer shells. And also these other electrons here are sort of blocking, they're sort of soaking up the attraction from the nucleus a little bit. So what the net effect is, the bigger an atom is, the more shells it has, the less electronegative it is. It's harder to influence electrons that are farther away. So the second trend has to do with going across the period. So let's actually dissect this before I actually reveal what the trend is. So if you look at, say, let's just go from let's talk about lithium, beryllium, boron, carbon, nitrogen, because I don't have room for all of them. So what's important to know is that lithium has 3 protons. Beryllium has 4 protons. Boron has 5 protons. Carbon has 6 protons. Nitrogen has 7 protons. So what happens is in all of these we're out in the second shell, and what we're doing is we're adding 1 more electron, but what's happening is we're also adding another proton. So what happens is these 3 electrons are better at influencing. Sorry, I'm drawing the right number of valence electrons on here. These protons are trying to influence this electron. These 4 are trying to influence these. Now, one thing is electrical attraction, electromagnetic attraction happens in all directions at once. It's not weakened by trying to attract 3 things in 3 different directions. It just exudes this attractive force. It's exactly like a magnet, right? So it's not splitting its power up over the electrons. It's just attracting these electrons. And what's happening is, as we add more electrons in one shell, we don't see, they're not getting farther away. And there are more protons in the nucleus to attract the electrons. And so what happens is, this is a more, and the electrons that are going to be coming in from another atom aren't any further away either. And so what's happening is you're getting more and more protons, and it's able to attract it more. And this really is why the noble gas configuration is so stable, because you have the maximum sort of attraction. It doesn't want any more electrons because there's no room. Adding another electron, when you go to the next shell, sort of resets the whole thing. Yes, sodium has 11 protons, but now it's way out there on another shell, and it just sort of resets back to the beginning. In fact, the electronegativity of sodium is going to be less than that of lithium. So the trend is electronegativity increases from left to right. So looking at the periodic table, electronegativity decreases going down. Actually, I'm going to write this differently. It increases going up, and we're ignoring the noble gases, and increases going to the right. So the most electronegative element on the periodic table is fluorine. This is why fluorine gets to bully everyone else. Fluorine is the best at taking away electrons, and the crappiest is down in this corner here. And you can kind of start to see why we have a metal, why when metals over here encounter nonmetals, the nonmetals just take electrons away from them. Whereas when you have nonmetals together, they have to share a little bit more because they have more equal electronegativities. Now, I don't expect you to know, I'm not going to ask you what has greater electronegativity, nitrogen or sulfur. I'm not going to expect that. So don't worry about that. I'm only going to expect you to know these 2 trends, and that's it. Okay. Oops. There we go. All right, so electrons spend more time near the atom with the higher electronegativity, and so that's going to be really important. I'm going to stop there. I just want you to be able to determine what's more electronegative. So a couple examples. So what's more electronegative? Nitrogen or arsenic? Oops, that's argon. Hopefully you said nitrogen, because nitrogen is higher up on the periodic table. What's more electronegative? Aluminum or carbon? And it should be carbon, because carbon is both farther to the right and in a higher group. What's more electronegative? Potassium or bromine? And it should be bromine, because they're both in the same group, but bromine is further to the right. So you should be able to predict what's going to be more electronegative. And I'm going to stop there, and I'll start a new lesson for the next